Welcome back. In this session, we'll learn how to realize a discrete time system. So let's start. So we know a digital system or a discrete time system is characterized or described by a different equation that looks like this is equal to v naught one. Sorry, let me put in one term here. And we say this is nth order difference equation which characterizes this nth order difference equation which characterizes this discrete time system. We can also write the above difference equation like this. In the form. So this is a difference equation which characterizes this discrete time system in time domain. Now the frequency domain realization of the same is we can obtain the frequency domain realization of the discrete time system by taking the Z transform. So taking Z transform on both sides, what do we have? Y, if we say Z transform of Y of n is Y of Z plus summation k running from 1 to m a k. Now if Z transform of Y of n is Y of Z, then Z transform of this term will be simply Z raised power minus k Y of Z, and this is because of the shifting property of Z transform. Same way the Z transform of the right hand side will be k running from 0 to m bk Z raised power minus k x of Z, where x of Z is the Z transform of x of m. So this is the frequency domain realization of the discrete time system or in Z transform, right? So we can obtain the transfer function model of this discrete time system. So we can obtain the transfer function model. How do we do that? By dividing output y of z by the input x of z. So we can get y of z above 1 plus just taking y of z common here, k1 and ak z raised to minus k is equal to summation k running from 0 to m bk z raised to minus k x of z. X of independent z is independent of k, so we can write it x of z. So or we can write it like this, dividing output transform which is yz by input transform which is x of z. This is referred as the transfer function of the system, and we can write like this, k running from 0 to m bk 0 is power minus k divided by 1 plus summation k running from 1 to m ak 0 is power minus k. So this is the transfer function of the discrete time system, which is described by this nth order difference equation. Yes, sir. Yes. All right. Now, to realize a discrete time system, before we do that, let's learn what are the different components that are used to realize or to obtain the structure of that discrete time system. You'll see this is the previous output of the system, and this previous output is multiplied by this quotient here. Same way, this previous output is multiplied by the quotient here. this output is multiplied by this quotient here. Same way, this input is multiplied by this quotient. This previous input is multiplied by this quotient, and same thing is true for this. So what is the first component that we require here is the multiplier. So we require multipliers to realize this discrete time system. So the first component is we require multipliers. Now how many multipliers do we require here? You can see 1, 2, so on up to n. So n multipliers are required for output, and how many multipliers are required for input? 1, 2, so on up to m. So it will be m plus 1. So m plus 1 is the total number of multipliers that we require here to realize this discrete time system. Now, what do we have next? We say we have output and this is the previous output. So to realize the system, we require a delay element, or we can say a memory element to realize this system. To store the previous output, we need to store this. Same way to store this previous output, we need to have a memory element. Same way to realize this to store this the nth previous value of the output, we need to store it. So we require a memory element, that's also referred as the delay element. So the second component that we require here is the delay element. Delay or memory element. Right? So we require delay elements. So how many delay elements or memory elements are required here? 1, 2, so on up to m. So m plus what are the memory elements to store the previous input? 1, 2, so on up to m. So m memory, m plus m memory elements are required. Now what is the third operation that we do to realize the system? We can realize sum. So there are additional elements. As we need to perform the addition of these inputs and outputs, previous inputs and previous outputs, to realize this system. So the third component that we need is the summer or adder. How many summers we require? There are n summers in this, and how many summers are there? M summers. So please check it how many n plus n plus 1 I think. Please check it how many are exactly required to realize this differential equation. Alright, or the differential equation that we. Now before I proceed, please remember now. So when we say the transfer function model of any system, discrete time system or a continuous time system, we can write it like this: 0 reduced by 0 plus 0 is by 0 is by minus 1, 0 is by b2, 0 is by minus 2, so on up to bm, 0 is by minus m divided by 1 plus a1, 0 is by minus 1, a2, 0 is by minus 2, so on up to an, 0 is by minus m. So this is the transfer. This is the expanded version of this transfer function. Alright, now the values of z which make this transfer function to equal to infinity are referred as the poles. Means when h of z is equal to h of z is equal to infinity, means the values of z which make this h of z to go below, to make it equal to infinity, are referred as poles of the system, are referred as the poles of the system, and the values of z for which h of z becomes equal to 0 are referred as zeros of the system. So from the sequence, means when the numerator becomes equal to 0, you can say these are referred as zeros, and when the denominator becomes equal to 0, these are referred as poles, because when the denominator is 0, this will be infinity. So in other words, we say it like this: when the transfer function is infinity or blows up, we say the values of values of z are referred as poles, and the values of z for which h of z is equal to 0 are referred as zeros. Right? So this transfer function has poles and zeros. In short, remember this: when the denominator becomes equal to 0, these are referred as zeros of the system, and these will give you the value. So zeros will be represented by this, and the poles are given by this, means when this is equal to 0. So this is how we determine pools and zeros of this transfer function. Right. Now let me illustrate this. Let me give a simple example. One. So let me give a simple example. Suppose the transfer function looks like this: z minus 1, z minus 2, and this is z minus 2, and z minus. So this is our system. Now you can see when z is equal to 1 or z is equal to 2 or both. So when this is 2, we know the transfer function will be equal to 0. We know the transfer function will be equal to 0. So z equal to 1 and z equal to 2 are the zeros of the system. So these are referred as zeros of the system because at these values the transfer function will become 0. Same way, when z is equal to 1 by 2 or z equal to 3 by 2 or both, then h of z will be equal to infinity. So these are the poles of the system, are poles of this transfer function. So these are the poles of this transfer function because at these values, the denominator becomes equal to 0, and when the denominator is 0, h of z will be infinity. So I hope you have got the idea what we mean by poles and zeros. Alright, now let me rewrite the differential equation again in the nth differential equation. This time I will write the current output on one side and the rest of the terms I will write on other side. So then it will be a1 y of n minus 1, a2 y of n minus 2 minus 1, a and y of n minus 1. Right? So this is our difference equation that characterizes or represents our system. Now, so we require three components to realize. So the first component is the delay element or the memory element. So the first element is the memory or delay element Now, how do you represent it or how do you realize this delay element? We represent it like this. We say, so we represent it as the inverse. Z inverse means delaying the input by 1 second. If the input is suppose x of n, output will be a x of n minus 1. Same way, the same system in frequency domain can be written like this. If the input is x of z, sorry, so if the input is x of z, then in frequency domain, then the output will be x of z inverse minus x of z, because this is the z transform of this is the z transform of this. So one and the same thing. Whether you say it in time domain, you say it like this and this. If you say the same thing in frequency domain, you write it like this. Now, same thing for the output means y of n. Same thing for the output y of n. Same thing we can write for the output y of n. So if the input is y of n, then the output will be, and the element is represented by this z inverse. So inside this box we write z inverse. This means delaying the input by 1. So output will be 1 of minus 1. Now the same thing in frequency domain. We write y of z, and the output will be z inverse y of z. Why? Because the same input in frequency domain will be y of z, and the output will be represented by, using the shifting property, it will be z inverse y of z. Or in short, we say that y of z is the input, output will be z inverse y of z. Alright, so this is the delay element. Now let me show you one more example of a delay element. Suppose this is our delay element. This box represents our delay element or the memory element. So if the input is now y of n minus 1, the output, if this is a delay element, the output will be simply y of n minus 2, means delaying the input by 1 sample time. That will be y of n minus 1 minus 1. So that will be y of n minus 2. Now the same thing In frequency domain, you can say write it like this: y z inverse y of z, and when you this can be written in frequency domain y of y z raised power minus 2 y of, right. Now see, you can write this expression directly. We know the output of the system in frequency domain is the transfer function multiplied by the input. So what I am saying, the output is input multiplied by the transfer function. Now the transfer function of this system is z inverse. So when you multiply input by z inverse, this will be z minus 2, right? In frequency domain, the output is simply as input multiplied by this transfer function, right? This is the output. So I hope you have got the idea of this delay element now. All right, so let me give one more example before I proceed. Let me give one more example. So if this is the delay element, so this is our delay element, and suppose the input this time is a2 y of n minus 2, right? So the output will be simply delaying this input by 1 instead of time. It will be a2 y of n minus 2 minus 1. That we can write as minus 3. Y of n minus 3. Now the same thing in frequency domain. We write it, the input is like this: z minus 2 y of z. Then the output will be this multiplied by this input, or simply the z transform of this. The z transform of this is right. So the same thing in frequency domain. So this is how we represent the delay element or the memory element. Now the second element that we require here is the multiplier. Now the multiplier notation used in discrete time is this. So the multiplier notation in discrete time used is. So this is the notation of a multiplier. So this is the input, this is the output, and we say if the multiplying values or the multiplying coefficient is a1, then the input is a y of n minus 1, the output will be a1 times y of n minus 1. Alright, so this does not delay the signal, it only multiplies the amplitude of the signal by this coefficient, this constant. Alright, and the same operation in frequency domain, you can write it as z inverse y of z. Then when you multiply it with a1, it will be y of z, a1 z inverse y of. So this does not do anything to the input, it only scales the amplitude. Alright, so one more example of this. So first the notation. Now the notation used is this. So this is the notation, and this is the input and output, right? And suppose the coefficient is b5. Then what will happen? And if we are multiplying x of n minus 5 by this coefficient, the output will be b5 x of n minus 5, right? So this will only scale the amplitude. So what is going on here in the frequency domain? We write it as z raised to minus 5 x of z. Then this will be b5 z raised to minus 5 x of z in frequency, right? So this is how we write the relationship of the multiplier, input output relationship of a multiplier in time and frequency domain. All right. And the last element that we need to have is the adder or the summer. Is the adder or the summer to realize this differentiation. Please pay attention to this. Why I'm showing you these components? Because to realize this discrete time system, which is described by this differentiation, I need to have these components. That's why I'm showing you these components. All right. Okay. So the next component that I require is summer. Now the symbol of a summer that's usually this. So the symbol of the summer is, so this is one input, this is another input, and this is the output. And suppose the input to the system is x of n, y of n. So the output will be in time domain x of n plus y of n. Right? Same output in the frequency domain, input output relationship, x of z, y of z. Then we'll say the input output relationship in frequency domain is x of z plus y of z. Right? So this is the summer. Now if I say one more example, if I say this is our summer, this is our summer, and this is the input. So the input to this is x of n minus 1, and the input here is a1 y of n minus 1. Let's take this. So the output will be simply sum of these two. So its output of the summer will be x of n minus 1 plus a1 y of n minus 1. This is just an example. Right? So the same input-output relationship in frequency domain. See, this is the input. This is the Z transform of this. Now the Z transform of this will be A1 Z inverse Y of Z. So the output in frequency domain will be Z inverse X of Z plus A1 Z inverse. So this will be the output in frequency domain, right? Now remember, if I say input in time domain is this and the input in frequency domain in this. Now can I do the addition of these domains? Can I do x1 of n minus 1 plus a1 z inverse y of z? I cannot do this. I cannot perform this addition operation because these are two different things. This is the description of the signal in frequency domain. Please remember that this is the description of the signal in frequency domain. This is the description of the signal, some signal in frequency domain. So you cannot add time domain description to the frequency domain description. I hope you have got the idea. So we cannot do that. Now let's realize this difference equation. So let's realize the difference equation, which is given by b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2 so on bm x of n minus, what is this, x of n minus m. Alright, then we have a1 y of n minus 1 minus a2 y of n minus 2 so on an y of n minus capital N. Alright, so how do we realize this? So what do we need? We need to have multipliers, delay elements, and then we need to add them, right? So first let me realize this part. So let's realize this part. Let's realize the input part. Alright, so suppose I have available this is x of n. So this is our x of n, right? Then what I am doing, I am going to delay this input by 1. So if I delay this, what I have at this will be x of n minus 1. Now what I am going to do to that x of n minus 1, I am going to multiply it by d1. So here I have x of n minus 1, right? Then I am going to further delay it. I am going to delay it. So the output will be x of n minus 2. So the output will be x of n minus 2. And I am going to pass this through a multiplier whose multiplying coefficient is b2. Then I'm going to further delay it, and the output will be available. Here is x of n minus 3, and I'm going to pass this through as multiplier. Write these values on this side. So this will be x of n minus 3, and I will pass this through a multiplier with a multiplying coefficient is b3 and so on. Right, so these are the, then this will continue, and finally the mth delay element. Mth delay element. So what will be this? This will be x of n minus n. And finally at this point I will multiply it with m, and this is the already part that I have now. And what I am trying to do here, I am trying to realize this input part. Right, that's what I am trying to do here. Right, so what I will do, I will add these here. I will add these here. So now I will use a summer, right? So first I will pass this add to this, then I will add this, then I will add this, then I will add this. So now I have realized this part. You can check I have realized this part. And because here what I have here, see, I don't pass it through this, so I will use summer here. Sorry, multiplier. I will use a multiplier here. Before I pass it, it will be V naught. So what I have here, this will be B naught x of n. Now here I have B1 x of n minus 1. Here I have B2 x of n x of n minus 2. Here what I have B3 x of n minus 3. What I have here I have Bn x of n minus n. Right? This is what I have available here, and this will give us this part. So this will give us this part. All right. Now I will realize this separately. I will realize this part separately first. First, let me assume that I have here y of n. So here I have y of n. So what I'm going to do, I'm going to delete. So let's delete. So if I delete what I have here, this will be z inverse. Z inverse means, so here I have y of n minus 1. Then I'm going to pass this through a multiplier whose multiplying value is minus a1. Remember that. Now I'm going to further delete. So what I have here, y of n minus 2. So if I delay y of n minus 1, it will be y of n minus 2. Now I will further pass this through a multiplier whose multiplication value is minus a2. Then I will again delete. And the output of this delay element will be y of n minus 3. Then I will pass this through this will be minus a3. Then I will continue this up to nth delay element. So I will continue this up to nth delay element. So what do I have here? Y of n minus n. And then I will pass this through minus a of n. So what I have here, are these multiplication constants what I have. So the signal available at this is minus a1 y of n minus 1 minus a2 y of n minus 2 minus a3 y of n minus 3 minus an y of n minus 2. Right? So now I will add these. So let me use a summer here. So let us sum this. And then I will sum this here. So this is sum, and this is sum. So this will give me y of, and this will give me actually this part. This will give me this part. Then I will add to this part. This is already realized here. Then I will add this to this part. This will give me y of n. Please have a look. Have I done it correctly or not? Right. So what I did first, I realized this part separately. So I realized this part. Then I realized this part. Then I added the two. First I realized this part. Now this is here. This part is realized here. So this is realized in this, right? Then this second part is realized like this. We realize it at like this and obtain this part. Then we added it to this part that's already realized here, and we obtain y of n. Have a look at this. Please pay attention. Have a look at this. So this is how we realize this discrete time system, which is described by this general nth order difference equation. All right. I hope you have got the idea here. Now in the next session, what we'll do, we'll see if we change the order of these poles and zeros. Where are the poles and zeros? This. If we interchange the order of these poles and zeros, what will happen to the structure? What will happen to this structure? Yeah, right? That we shall learn in the next session. Remember, x of n is the input, y of n is the output, and z inverse these small boxes are denote and the delay elements. These denote multiplication elements, or the multiplier simply. This is the summer. Finally, this is your output. All right. Okay, now before I end this session, please remember, have a look at this. You can see the y part actually. So y part of the expression, means this part. This part actually gives you the poles. Please pay attention. See the if you see the y part, means if you see this general uh, this this transfer function of this system, then ak minus v inverse, right? See, this part comes from this, right? This part comes from this, and this part comes from this. So the numerator part is associated with this previous inputs and present inputs, and the denominator part is associated with the previous outputs, right? So the poles are determined by the previous outputs, in other words. So the poles are determined by previous outputs, are simply outputs, previous plus present, previous plus present outputs, and the zeros, you can check it, are determined by the present and past inputs. Please have a look at the difference equation you will get, because these coefficients are associated with the past outputs, and these coefficients are associated with the present and past inputs, right? So you can have a look at this. Now in the next session, what we'll do, if you interchange the order of this and poles and zeros, what will happen to the structure here? What will happen to this structure here? Please pay attention how we have realized this. In the next session, we'll see the if we interchange the order of this. If you interchange the order of these poles and zeros, what will happen to this structure? All right, let me end the session.